Okay, thanks everyone for coming to this week's C3 AI Digital Transformation Institute seminar. The C3 AI DTI mission is to attract the world's leading scientists in a coordinated and innovative effort to advance the digital transformation of business, government, and society. And in particular, this weekly seminar will focus on interdisciplinary work that joins the effort from machine learning, computer science, operations research, and engineering systems. We want to thank our academic partner, the High Performance Computing Support, as well as the industry partners for the Institute. We're approaching an end to this series on incentive design and learning for societal systems. And we're very excited to conclude this seminar series with today's talk from Chinmay. And if you have missed our talks in the past few weeks, please go check our website and check our YouTube channel. We have all the talk videos as well as the slides posted there. Also, we won't have the seminar series for the summer, but please stay tuned for our series in the fall. Okay, we're very excited to have Chinmay Maheshwari to present his work on decentralized communication and coordination-free learning in structured matching markets. Chinmay is pursuing doctoral study at the University of California, Berkeley, under the supervision of Professor Shankar Sastry. Chinmay received his Bachelor of Technology and Master of Technology degrees from the Indian Institute of Technology, Bombay. His research focuses on using tools from game theory, control theory, online learning, and optimization for the design of robust and efficient societal scale systems comprised of strategic and adversarial entities. As usual, we will have a 50-minute of presentation followed with 10-minute Q&A, and please use the Q&A feature to ask questions. And so Chinmay, the floor is yours. I will stop sharing and you can open your video and unmute yourself and share your screen. Thank you.
Thanks, Manshi, for the invitation. It's really an honor to present at this platform. Okay, can you see the slides?
Yes.
Okay, thank you. So hello everyone, I'm Chinmay, and today I'm going to talk about one of our recent works which lies in the area of learning for matching markets, and we are specifically developing decentralized communication and coordination-free algorithms. This is a joint work with Professor Eric Majumdar and Professor Shankar Sastry. Eric is professor in Caltech and Professor Shankar Sastry is at UC Berkeley. Okay, so it's not wrong to say that today we live in the age of algorithms. For every task, we will have different algorithms surrounding us, be it recommendation systems, be it navigation systems, and a lot of these things. So it becomes of utmost importance to think about the fundamental properties which help us in design of efficient and robust algorithms in such domains. However, in a lot of machine learning algorithms or machine learning research in this area has focused on a single agent who is learning its preferences by repeatedly interacting with an environment which is assumed to be static. And people have developed, it's been like more than 2 decades when we are studying this problem in the bandits and reinforcement learning lab, where we have developed optimal algorithms which trade off the exploration and the exploitation aspect of the problem in a very efficient manner. However, the problem in which once we move from one agent to multiple agents is not very well understood. So usually if there are multiple agents, that leads to competition, and competition leads to externality in the learning of any particular agent. Specifically, this externality is exacerbated when we have some scarce resource which needs to be competed for. And in fact, we have seen some examples where these algorithms which are used in high frequency trading application can lead to a very weird market phenomena which can lead to crashes and all. So it becomes utmost importance to think about the competition of these algorithms from one another for each other in a market. So we need to develop algorithms which can explore efficiently for the new information, which can exploit for the available information, and which can compete effectively while also accounting for other strategic entities in the market. So in this talk, I'll focus on the setting of a two-sided matching market. Broadly speaking, the problem which we will discuss today is based on how can the agents on one side of the market who do not know their preferences over the other side of the market learn in an efficient way while also competing for the scarce resource in the market, which is like which is matching with the other side of the market in an efficient manner. So there are several emerging two-sided matching markets in this online domain, which include companies like TaskRabbit, Amazon Mechanical Turk, DoorDash, etc., to name a few. And these encompass domains like online labor market or online dating platform, etc. So right now, I'll just try to abstract out the problem of matching market. So what are matching market at the end of the day? Matching market is nothing but it's a set of agents A and a set of firms F. And each side of the market, so agents comprise of one side of the market, firms comprise of the other side of the market, and each side of the market have preferences over one another. A matching is defined as an injective mapping, which maps each agent to a firm on the other side of the market. So this is one particular example of matching. An important concept in this domain, which defines what is a suitable matching, is that of a blocking pair. A blocking pair is a tuple of agent and firm, such that both of them prefer each other over their current matches. So in any matching, we call an agent a tuple, agent firm tuple A comma F to be a blocking pair if both of them prefer each other over their matching which are proposed in that matching. Okay, so a solution concept in these matching market is that of a stable matching. So we call a matching to be stable if there exist no blocking pairs. Okay. So to give an example, so consider the same market which I shown on the previous slide. Here we see that A1 and F1 form a blocking pair because both of them prefer one another over their current matches, which are F2 and A2 respectively. However, this is an example of stable matching as you cannot find any blocking pair. Interestingly, Gale and Shapley in 1960s started to study this problem under the name of stable marriage problem. Sorry. But that is essentially a different name for the same problem. And they showed that the stable matching always exists, but however, it can be a non-unique. It's not sure that it will always be unique. So now the question of how can we come up with a stable match? These guys, Gale and Shapley, described an polynomial time algorithm, which goes something like that. Every agent kind of starts unmatched, and then an agent queries its most preferred firm, which has not yet rejected it. And then firm reviews list of all the queries it has received and forms a tentative match to the best agent who has queried that particular firm and rejects all other agents. And the same process goes on and on. And it can be shown that it can always converge to a stable match. I would like to draw your attention to the properties of this interesting algorithm. In fact, one can observe, like the way the algorithm described on the previous slide, it is a decentralized algorithm. So each agent is making its own decision. No one is coordinating it to what to do. There is also no communication between agents about what was the last place they got rejected from, or what was the last place we got tentatively matched on, etc. And in fact, we have good convergence properties to a stable match. So the goal in this talk is to develop an algorithm that does the same thing which a Gale Shapley does, or preserves all these properties of decentralization, communication-free, and coordination-free properties, while also learning the preferences of the agents. And one has to do it in a data efficient manner as well. So let me now elaborate the setup a little bit more. So we have a set of agents denoted by A, set of firms denoted by F, and they form a market, which is nothing but a combination of agents and firms. We assume that firms have a fixed but known preference over agents. However, the agents do not have a known preference, but however, their preferences are fixed over the firms. In order to learn the preferences, agents will repeatedly query the firms. And in this process, they will receive some noisy utility based on a successful interaction with the firm. And the noisy utility is denoted by this big U. And epsilon here is, for the purpose of this talk, we can assume it is a one sub-Gaussian noise. And little u is a mean reward, which is unknown. Just introduce a few notations. We call a firm queried by an agent A at time t by fa of t. And the set of all agents who arrive at firm f at time t, we denote by a f of t. Okay. So now in this model, what is the utility an agent? What is a utility an agent will get if it queries a firm? So utility of agent depends on two aspects. One is the noisy utility which it gets. Plus, it also depends on what other agents have also applied to that particular firm at that instant of time. So that leads to a lack of the information which agent has. Agent does not a priori know which other agents have applied there. So this parameter YA captures that phenomena. In particular, YA we assume is a 0-1 variable. It takes value 1 if agent A is the most preferred amongst all of the agents who have applied at that particular firm FA of t at that instant of time. And we assume that the variable YA is 0 if it gets collided or it gets rejected by the firm, simply because there is someone better than this agent A who has applied, so the firm prefers that agent over this one. For the purpose of this talk, we assume a unique stable matching, and we denote the stable matching of an agent A by F star of A. Okay, so what is a good performance measure to kind of quantify the performance of any algorithm we design of how agent choose which firm at any instant of time? So here we consider a performance measure which has been recently introduced in some of the papers, which I will elaborate later on, which is about that of a stable regret, which is nothing but it compares the performance or the total reward an agent would get had it known its stable match vis-a-vis how much reward it gets based on whatever algorithm suggests to it. So the second part, the big UA of t, denotes the reward which is suggested by the algorithm, and UA of F star denotes the expected utility which it gains from matching a stable match. Okay, so there has been a flurry of research in past couple of years in this area, which has tried to look at some versions of this problem, and I'll just want to compare these problems, those versions, with the one which I will present today. So Liu et al. In 2020 presented a centralized setting where agents will submit rankings to a platform, which then platform would then recommend which firm to query to a particular agent. They assumed a generalized market structure in the sense they do not assume any structure on the preferences, and they are able to show a regret which grows polynomially in F and logarithmically in time. There was other paper, Sankaraman et al., who relaxed the centralized assumption but assumed some sort of a global communication which happens between players. And they assumed that the preferences follow what is known as serial dictatorship, which is a condition in which one side of the market has same preference over the other side. Like each agent in that particular side will have same preference over the other side of the agent. And they showed a regret bound which grows polynomially again and logarithmically in time. Liu et al. In 2021 then presented a decentralized version of this problem, where the agents could observe who other, can observe other agents who collided with a particular firm at any instant of time, or they observe all other agents who got collided with them when they approached any particular firm. And under a generalized market structure, they showed a regret bound which goes exponentially in f to the 4 and quadratically in the log. I would like to note that they presented an agent passible regret, which means the stable match they consider because is not unique because it's a general market, but they consider a stable match which is the worst for every agent. Basu et al. In 2021 presented a decentralized algorithm which does not need any communication or any observation of what other agents are playing, but it requires some sort of a coordination of players or some initial coordination between players, which led to some of these phase-based algorithms. And they show that they can achieve a bound which grows again logarithmically in time horizon, but now they have a better regret, like a more stronger notion of stable regret, which is that of agent optimal regret. And under a more refined structure, which they call uniqueness consistency, they kind of even reduce this log to the power of 1 plus epsilon to log of t. So uniqueness consistency is kind of a necessary and sufficient condition which ensure unique stable matching in a market. So against these works, in this work, we presented an algorithm which does not require any coordination, does not require any communication. Each agent runs these algorithms at their local end based on only the information of past interaction of their own past interaction with the firms, and does not need any other information. We do impose an assumption that the market has a unique stable match. More particularly, we assume what is known as the alpha reducibility on preferences, which I will highlight in later slides. And I will also elaborate the applicability of our algorithms in more general markets, although we do not have a theoretical results for that right now, which I'll also allude later on. So the good part is, and even under this setting of decentralization, no communication and no coordination, we are able to achieve a logarithmic regret in time, and which only goes polynomially in the size of the firms. I would like to note at this point that the algorithm which I present is built on a novel combination of a stochastic bandit algorithm with an adversarial bandit algorithm. I'll describe this more rigorously in the later slides. I would also like to point some other related works which lies in the area of bandits with collision, where there are multiple players who choose particular arms on the other side, and when there is a collision, no one gets any reward. There are other settings of centralized platforms where agents follow recommendations from a platform while the platforms are learning about the preferences of agents. And there are some other slightly related work on competing bandits, which kind of describe how the exploration goes hand in hand when there is a competition. Okay, so coming back to our problem structure, I'd like to highlight what are the main challenges which we face in this setup. So if you remember, the utility which any agent gets at any time is dependent on and noisy feedback, which is denoted by this UA, FA of t, which is term in blue. And then there is a collision term, YA, which describes who other agents have applied to that particular firm. And this leads to some sort of a non-stationarity in the process, in the reward distribution, which any agent gets at any instant of time. Moreover, our requirements of the algorithm being decentralized, communication and coordination free is also needed. And these requirements are needed to ensure the scalability or the privacy and the robustness of these algorithms. Okay, so let me highlight how people typically handle uncertainty in in a machine learning world, it's typically handled by the stochastic multi-arm bandit, where we assume there are multiple options and each option will give us uncertain reward based on some static distribution. And a performance measure used in this literature is that of a regret, which compares the performance of any algorithm with the best possible arm, with the scenario in which agent chooses the best possible arm amongst all. There are several efficient algorithms people have developed, which are upper confidence bound algorithm, Thompson sampling algorithm. Just to quickly give an idea of what these algorithms look like, the upper confidence bound algorithm basically keeps an optimistic estimate of the mean reward of every arm, which is based on an empirical mean term, which is computed based on the past interactions, plus an exploration bonus, which depends inversely on the number of times an agent has chosen a particular arm I. So the exploration bonus kind of denotes some sort of a confidence interval around the empirical mean. So algorithm is simple. At every instant of time, it chooses the firm with the highest upper confidence bound, gets feedback, updates these estimates, and repeat the process. The proof of these algorithms is based on concentration of measures. And people have shown that these algorithms are optimal in some sense, in that they achieve a log t regret bound, which is a very slow increment in terms of t. Okay, so uncertainty in our scenario, we again use some sort of a stochastic bandit module to capture the uncertainty. However, to capture the non-stationarity and the other design requirement of decentralization and communication and coordination free algorithm, we propose a new algorithm design, which is as follows. So the algorithm goes like this. At any instant of time, every agent is using this algorithm, and every agent is forming an ordering of firms. And this ordering is again based on some UCB estimate, as I presented before, or it can be based on some other estimate like Thompson sampling index and whatnot. And this ordering is denoted as a figure on light. For example, in a simplistic toy example, let's say with 3 firms at any instant of time, agent A, the ordering for agent A looks like the firm 2 is preferred, then firm 3 is preferred, than firm 1. Once the agent has these orderings, agent goes over these firms one by one and flips a coin with or flips a biased coin with some success probability, which is denoted by PS. I'll elaborate more on how these PS, these success probabilities are computed. But for now, I'll just mention that these success probabilities are computed based on some adversarial bandit algorithms. So once an agent flips a coin, if it receives a success, then that means the agent proceeds with that. And then the agent chooses that particular firm at that instant of time. If it leads to failure, which we'll call as the agent has pruned that arm at that particular instant of time, it will move to the next best option, which is F3 in the scenario, and repeat this process again and again. In the rare scenario, when all of the firms gets pruned, or all of these coins give us failure, then we simply choose the firm with the highest indexing at that instant of time, and the agent will play that particular firm. Okay, so on a high level, the algorithm paradigm looks something like this. We have combined a stochastic bandit algorithm with an adversarial bandit algorithm. So for every firm, an agent has an adversarial bandit algorithm which decides these success probabilities, which were discussed on the previous slide, and uses that to decide which firm it will query at that instant of time, or which firm it will request at that instant of time. And similarly, if all the agents submit this in the market, then naturally there will be some collisions, there will be some matchings, and out comes some more information which is used to update these specific module, the parameters in these specific modules. So as I promised, I will describe how do I compute these success probabilities. For that, so for now, just consider that we are using some sort of an X3 based adversarial bandit module. X3 is a very famous adversarial bandit algorithm. And for any firm, the agent has to decide between two options. Either it has to query that firm and put that in the market, or just prune that and find the next best option. In this process, we define these loss functions of this bandit algorithm, something like this. If the agent prunes that particular firm, then it gets a loss of 0.5. However, if it decides to query the firm and from the market it sees that there was a collision, then in that case it will incur a loss of 1. If there was a successful match, it will incur a loss of 0. So following an X3 module, we can decide, compute all of these loss estimators, which these algorithm X3 maintains at every instant of time. And using these estimators, we compute these success probabilities. So a notion of performance in these adversarial bandit algorithm is that of adversarial regret, which computes the performance of the algorithm with the best fixed action in hindsight. So the first term here, LADVITT, denotes the loss adversarial bandit incurs in t time steps. And the second term denotes the loss any fixed action incurs in t time steps. And it has been shown that this X3 algorithm will incur this regret, which grows in square root t fashion. Okay. So with this knowledge, I would like to point at this moment that in this paper, we do not present any one single algorithm. We present a class of algorithms. So in this stochastic bandit module, we can choose any of these algorithms such as UCB or Thompson sampling algorithm. And for the adversarial bandit module, we can again choose any adversarial bandit algorithm of our choice, for example, X3, or some more sophisticated algorithms, which I'll allude to later on, which goes by the name of adaptive algorithms. So it's not really one algorithm, it's a class of algorithms which we discuss here. And the algorithmic structure is modular. Okay, so let me present the results which we get in this setting. So as I stated in the initial slides, that we assume some sort of a uniqueness condition on the stable matching. More particularly, we assume this assumption that the preferences are governed according to this alpha reducible assumption. So what is this assumption? This assumption basically says that, to define this assumption, let me first describe what is this one technical term, which in the matching literature, which goes by the name of fixed pair. The fixed pair, we call a tuple A comma F to be a fixed pair if F is the most preferred agent by A, and A is the most preferred F is the most preferred firm by A, and A is the most preferred agent by F in any market. I'll describe it with a toy example in the later slide. And we call a market to be alpha reducible if every submarket has a fixed pair. So to understand this definition more carefully, let's look at this toy example where there are three firms. Agents have these preferences over firms, which are denoted at the bottom, and the firms have preferences over agents, which are denoted at the top. So in this preference order, we see that the most preferred agent for A1 is F1, and same holds for F1, that its most preferred agent is A1. So we call A1 F1 here is a fixed pair. So let's just kick those pairs A1 and F1 out of the market, and we get a sub-market, which is a subset of original agents and firms. And still here we see that in this sub-market, the new fixed pair emerges, which is A2 and F2. Note that A2 and F2 were not the fixed pairs in the original market. These only emerge after these A1 and F1 are out of the market. But note that A3 and F3 is not a fixed pair still. And again, if we kick out A2 and F2 as well, we are just left with one choice. So this is trivially a fixed pair by definition. Okay, so let's look at some properties of these alpha reducible markets, which are helpful in the analysis. So number one question of why these alpha reducible markets matter. So an example of alpha reducible market is in the setting where, for example, consider a setup of online labor markets where there are employers on one side and employees on the other side. So you can consider employers as the agents and employees as the firms. Employees will naturally have some sort of a fixed preference over which firm they want to work with because of some common societal knowledge which they have. So for example, I want to work more for firm A than firm B and then C. So this kind of ordering is kind of fixed for all of the agents. So that kind of market comprises of an alpha reducible market. But those are not just the only alpha reducible markets. Alpha reducible markets are more weaker than just that. So one of the properties of these alpha reducible markets is that it allows us to do a particular partition of the agents and firms, as we saw in the previous toy examples. So more particularly, it looks like that the set of agents A, I can partition it into disjoint unions of AIs, which I'll describe what these unions are. And we can similarly partition the set of firms into these FIs. And we call a market MI as just the union of all of this AI FI for, oh, sorry, I think there's a typo. It should be all of AJ union FJ, where the union is taken over all of the J greater than I. So essentially what AI FI pair constitutes is the set of agent firm players, which are fixed pair in this market MI, which I defined. So in the previous toy examples, A1 could be just a set of agent firms pair A1 F1, which was the first market. And then A2 could be the second tuple A2 little f A2 F2, and so on and so forth. Okay. And also one can show that these alpha reducible markets have are sufficient conditions to ensure that the market will have a unique stable match. Okay, so once we have a stable match, let me just define two more terms, which are helpful in describing the later analysis. So we call F star of A as the stable match, as I alluded before. We denote this F sub bar A to be the suboptimal firms, which are all of the firms which an agent A prefers less than its stable match. And we define this notion of super optimal firms, which are all of the firms which an agent A prefers over its stable match. Okay. So precisely because there exists some super optimal firms, agent A will always want to go to those super optimal firms, but simply those super optimal firms prefer some other agent over this agent. So then this that agent will see some collisions, and that is not a fruitful information which they get. So to see this, let me just provide main results, and these properties of alpha reducible will become more clear in our analysis techniques. Okay, so our main result goes something like this. In the algorithm pipeline, which I presented before, which combines the stochastic and adversarial module, if, for example, I choose a UCB or a Thompson sampling as the stochastic module, and if I choose, let's say, the X3 algorithm as the adversarial bandit module, what we can show that the stable regret only grows square root t in the time horizon, and it grows only polynomially in the number of firms, and has this natural 1 over delta square dependence, where delta is nothing but how much gap or how far is any firm F from in terms of reward from the stable match, which is described below. So these delta terms are kind of like the staple thing in the bandit, stochastic bandit literature. Okay, so we see that is this result, when we see this result, we ask a question, can we do better? Simply because we are getting a square root t regret, which also depends on instance. that is, it also depends on delta. So that is not a very good proposition for us, although this regret is a suboptimal regret, sublinear regret. We still want something better. And question is, can we do better? And I say yes, and we can do this better by using some information about collisions in our adversarial bandit module. So right now, the adversarial bandit module is does not depend on what exact data any agent sees. Even if an agent is in a benign environment, it assumes that the adversary is governing its losses, and that's why we are not getting a very, very efficient algorithm. So to overcome that, we use some of the recent results which are published in this domain of data-dependent regret bounds for adversarial bandit algorithms literature. So these algorithms typically go by the name of mirror descent with log barrier regularizer, which was proposed in this paper of Luo et al. In 2017 and was improved in the paper by Bebek in 2019. So using these adversarial bandit algorithms, we compute now the success probabilities. And it turns out that these algorithms compute success probabilities by doing a regularized optimization over the loss estimator L hat query and L hat prune. And these loss estimators are also constructed in some very specific manner, which depends on adding some corrective terms and adding some optimistic estimates. It's not the usual estimator which we see in the X3 algorithm. But what is so interesting about these algorithms is that these algorithms can give you regret bounds which are much better than square root t. So in fact, we get here, these algorithms obtain a log t regret bound. But also these regret bounds depend on the path length. And path length is something which depends on the exact data which comes from the system. So path length is defined as at any action AT, at any action AT minus 1, what is the difference in the loss I would get at the same action between two time steps. Sorry, I think there's a typo. It should be LT of AT minus 1 and LT minus 1 of AT minus 1. So it compares the loss at two different time steps of the action which you selected. And if your environment is benign, for example, if the loss does not change a lot, then we can expect this path length term to be small. And this is precisely the property which we exploit in our analysis. And in fact, what we can show that if we use this mirror descent based algorithms as an adversarial bandit module, then we can obtain a regret bound which only grows logarithmically. So in a sense, I'm saying that we can control the path length term very specific, very precisely, and so that we can just retain the log t bounds for those algorithms. And same, we have the polynomial dependence on the number of firms. Okay, so before proceeding to proof, I'll just pause for a sec, and if there are any questions, I'm happy to take now.
I have a couple of quick questions. So you assume an asymmetry in the information, right? So agents don't know the utilities they'll get from firms, but the firms know something about agents. Is that correct?
Yeah. Mm-hmm.
Okay.
Yes.
And then on top of that, you make this uniqueness assumption on the alpha matching assumption. Okay.
Yeah.
I guess maybe after the proof, it'll be clearer why you require these, and what would be the challenges.
Yeah. I'll describe these important in the proof.
Okay.
Yeah.
I'm curious also about the theorem. You give a log t type of result divided by delta squared. This is sort of what people would call the instance dependent bounds, right?
Mm-hmm.
I guess that's because you're using UCB or Thompson sampling, whereas for the tossing the coin to figure out whether you're going to consider a firm or not, you're using adversarial.
Mm-hmm.
Right. So somehow that part is adversarial. The other part is stochastic inspired by stochastic bandits. And so that's the reason you get the log t here, right?
Yeah.
Okay.
And also, if we use this data dependent algorithm, this log t is also a characteristic of that.
Okay. Okay.
If we control the path length properly.
Okay.
So in the previous algorithm, if you were using x3, the square root t was a dominant term,
Right.
and that's why we get a square root t regret there.
Okay.
Yeah.
Okay. Okay. Thanks.
Yeah. Thanks for the question. Okay. So let me describe the proof, I guess, in next couple of minutes to see where all of these structure, like how does this whole picture, on a big picture level, how does this all things come together? Okay. So if you recall, the utility which any agent gets at any instant of time is comprised of two parts. One is the stochastic element, which is denoted by this first term UAFA. And then there is some non-stationary element YA, which kind of depends on how other agents are exploiting the environment. So if I write the regret, which I described, the stable regret, which compares the performance of this algorithm with always choosing the stable arm, I can decompose this regret into two terms. The first term is on all of the time intervals when y was 1, that is agent was successfully matched, plus all of the time intervals where y was 0, where the agent was not successfully matched and it was rejected and it collided. So in fact, the first term, when it was always successfully matched, we can, using the same regret decomposition which we see in stochastic bandit algorithms, we can decompose it in terms of the gap times the number of times agent matches with a particular firm, which we denote by MAF in time t. And the other term, which is always a constant regret, which we get because of UAF star, because we collided and we get no extra reward out of that time interval. So we'll get that constant times the number of collisions in t time steps. In fact, as if you recall, we showed that because of this uniqueness assumption, we can decompose the set of firms into the set of suboptimal firms, set of superoptimal firms. So I would like to note that the set of all superoptimal firms will give me a negative regret, simply because the delta is negative, because I gain more reward on matching to those firms than my own stable match. So I can just trivially upper bound this regret. So only things which I want to worry about right now is the matchings with the suboptimal arm and the collision with the arms. Okay. Okay, so let's try to look at what kind of properties or theoretical property these adversarial bandit regret gives us. So if you recall, this was our loss structure. On successful matching, we get 0 loss. On collision, we get 1 loss. And on pruning, we get 0.5 loss. So if I chuck that then into the definition of regret of an adversarial bandit algorithm. So if we consider the case when always pruning was the best fixed action in hindsight for that algorithm, then in that setting, the regret converts into just the difference between collisions and matchings, simply because of the loss structure here. And we know that this is always bounded by the adversarial regret. So in the x3 case, it is square root t. In the adaptive algorithm case, it's log t plus the path length. Besides, if we consider the other case where always squaring the firm or always choosing the firm is the best fixed action in hindsight, then one can decompose on a high level, intuitively speaking, this regret term into two terms, which are the number of bad prunings plus minus the number of right prunings. So number of bad prunings, I mean just whenever the firm was pruned, when it should not have been pruned, simply because algorithm just miscalculated that it will face collision, so I should prune it. And thereby right pruning, I mean at all of the instances when the algorithm correctly pruned the firm, simply because there was other agent or other more preferred agent at that particular firm who was also selecting that. So the firm this particular agent will get a collision. So it kind of rightly prevented that scenario. And again, we can show it is bounded by the adversarial regret. So a key takeaway from this slide is that one can bound the number of collisions by the total number of matchings plus a regret term of the adversarial bandit algorithm. And also we can bound the number of bad prunings by number of right prunings plus an adversarial algorithm term, adversarial regret term. Okay, so using this, if I chuck that into my regret expression, which I presented on the previous slide, so I just want to eliminate all of the collision terms in the regret expression by just replacing them with matchings and the adversarial regret part. So all in all, I've reduced the problem to just worrying about the matchings, the matching of these firms. Okay, so now we consider the matching, bounding the matchings. Okay, so the number of matchings, let's first try to bound the number of matchings with a suboptimal firm. So this kind of analysis, as you'll see, kind of resembles a bit with analysis of any stochastic bandit algorithm, simply because on suboptimal firms, you can get rewards easily. So just writing out the expression for number of matchings, which is an indicator variables, which indicates whether you matched, and an indicator variable which resembles whether you selected that particular firm. So we can decompose this event into two parts. The first part is number of times the index of that firm F was actually better than the index of the stable match. Okay, and the other event is number of times the index of the stable match was good, but simply because the adversarial module kind of pruned it, the firm F got a chance to be played. So if we look at the first term, which kind of resembles in the stochastic bandit module, we see that when a suboptimal firm or when a suboptimal arm in stochastic bandit is better than stable match, we decompose it into two events. First event is we ask the question, we consider the scenarios where the index of that particular firm was an overestimation, and we use some concentration inequalities to bound that. And we consider another scenario where the stable match was unfortunate, that we have a very underestimation of the reward of which we get from stable match, and that's why firm F had a better better index, a better ordering. So these all terms can be bounded by concentration inequalities. If we look at the number of times an agent prunes a stable match, in those scenarios, we can decompose it into two scenarios. One is the number of times there is a right pruning, in a sense that it prunes a stable match at the correct time so that it does not face a collision. And then there are bad prunings, where it just prunes a stable arm, but had it played it, it would have received a reward out from it. So we bound this term using the adversarial bandit algorithm. If you remember from the adversarial regret, we bounded that the bad prunings are never more than the right prunings plus a regret term. So bearing all of the constants, we can bound the sum of right pruning plus bad pruning by just a constant times right pruning plus an adversarial regret term. Okay, so now here we now have to consider how to bound the number of times we did a right pruning, and that's where we use alpha reducible structure. Okay, so what do I mean by right pruning? In words, right pruning means that there exists another agent which is more preferred by stable match or stable firm, who is also applying to that particular firm. So that is what a right pruning means in words. So, and here we use the structure of alpha reducibility. So one of the properties of these alpha reducible markets is, if you remember, this alpha reducible allows us to partition the market into several these AIs and FIs. And we can show that if there is any firm which lies in this F of I, then the stable match, so all of the agents which are more preferred by a particular firm F, then its own stable match are all of the agents which are belonging to higher up in the market, which are belonging to all of these partitions which are lying before ith partition. Sorry, I think there's one more typo about this. It has to be AJ. Sorry about that. So now we do this in a recursive manner by following an induction argument. If you look at the agents which are always in the first set, which is A1 set, then there is For them, all of the firms are suboptimal firms. There is no super optimal firms for them because simply because they are matching to their fixed pair, which is the best possible option for them. And in that case, this right pruning quantity will be 0, or this event is empty set. So you can bound the number of times any agent in A1 matches to its suboptimal firms. We then follow an induction argument similarly for any set EI. The number of times using the lemma above, we can show that the number of times any agent has applied to its stable match is bounded by number of times any of the agents in the higher up markets have applied to their suboptimal firms, because those are the only agents who are more preferred by that stable match of that particular agent. So we have all, and for those agents, that particular stable match is a suboptimal firm. Because of the alpha reducibility structure. So if we follow this induction argument, we have only one by one going from A1 to A2, so on and so forth. You bound the number of suboptimal arms, and you can get bound on this term following an induction argument. Matching with super optimal arms also follows similarly. I guess in the interest of time, I'll just skip this slide a bit, because this again follows from the same idea of doing induction by using the partition which is created by this alpha reducible structure. And yeah, let me just skip it, but the whole idea lies the same, that you just use that partition which is created by the alpha reducible structure. And because of that partition, some of the agents will learn quicker as opposed to other agents. And the agents which are lying below in that alpha reducible structure are kind of in their stable match can only get collided because of the agents lying above them. So it's kind of induction argument based on this partition which I described. So let me just quickly wrap up in a couple of minutes. Let me just present some numerical examples. So we simulated this thing for an alpha reducible market for 5 agents, 7 firms with fixed preferences. And I mean, we did a little bit more fancy algorithm where each agent either chooses Thompson sampling or UCB by randomly flipping a coin. And you can see, and all agents use this mirror descent kind of adversarial bandit algorithm. So you see this, the green arrows denotes the matching and the red arrows denotes the collisions. So you see initially there are a lot of collisions because all of the agents are kind of learning. And eventually these agents kind of decide on what are the best possible arms from them, and they converge to the stable match. Now there is a question about, can the alpha reducibility assumption be dropped? In fact, we have seen in simulation, if we just randomly generate preferences and ensure that it is not stable match, it does not satisfy alpha reducibility, even then these algorithms kind of behave in a very nice manner, that these regrets kind of do not, it kind of behave similarly to how these alpha reducibility structures perform for with alpha reducible structure. And these confidence bound here just denotes the run of these algorithms over 25 iterations. Okay, so in conclusion, we presented an algorithmic paradigm which provides a decentralized learning where an agent does not need any communication or any coordination with any other agent in a structured matching market. And we presented a bunch of algorithms or algorithmic pipeline which we can plug in variety of algorithms and work and see what works best for you. In fact, we presented optimal rates in some sense in terms of the time horizon, because even in the single agent setting, we know log T is kind of the best possible rate, but people have shown lower bounds in terms of log T. This brings me to the last slide about future research in this direction. I still believe we can, of course, expand to the other market structures, which are way more weaker than the alpha reducible structure, as our numerical simulation is suggesting. But also there's a need to develop a tight bounds, lower bounds on how, what is the dependence on the number of agents, a lower bound on how the number of agent depends, or how the regret depends on number of agents. The there are several interesting situations as well, because in real life, it's not just only one side is learning. A lot of time, both sides of the markets are also exploiting hand in hand and competing with their counterparts in their particular side. So it becomes interesting to also consider the question of these decentralized question in this setting in which both sides is learning. Also, the question about, can the system be gamed, in the sense that if everybody is using this decentralized algorithm, can I smartly use some other algorithm which gives me a better regret bounds? That's an open question. Also, the question about these preferences are, the preferences cannot change a lot between me and my friend, because we live kind of nearby and we share some of the common opinions. So the question about how can you use some context to come up with these algorithms in a contextual bandit setting. And besides, the preferences of human beings do change. It's not always stationary. These preferences can change due to some environment evolving. We see my preferences today will be different than what I had preferences last year. So these kind of drifts in preferences should also be accounted by these algorithms. With this, I'll conclude. Sorry for going a little bit over time. Yeah, please feel free to send me any comments, questions, thoughts.
Hi, Chinmay, thanks for the great talk. So we are open to the Q&A sessions. If the audience has questions, please type them. For the panelists, if you have questions, please just unmute yourself.
That's good. This is just have a picture of you there.
Okay. Okay, yes, thank you. So I have a small question about my speaker is not working. Can you hear me?
Yeah, I can hear you. I can hear you.
Yeah, so in each round of your algorithm, it seems like you need to have a few rounds of proposing and to decide if it is being turned down or it is being pruned, right? So, so this is kind of like then the definition of what is key. So I kind of think like this multiple rounds of proposing is considered to be just one step. So I'm not sure if I missed it or I got confused.
Yeah, I'll just go over the slide.
So I'm just trying to say that it seems the algorithm runs more than just the T steps.
Yeah, so this is like at any instant of time, these all things this agent is doing in his head in some sense.
Oh, okay, okay, cool. So only one feedback is getting.
Yes.
Okay.
It will only get feedback from what it plays.
Okay, yeah. Okay, that answers my question. Thank you. Thanks a lot. Any other people having questions? Okay, so if there's no question, I want to thank everyone for attending our last seminar of the series. Please stay tuned and subscribe to our newsletter for future events. Yeah.
Shrikant, you want to talk about the series in the fall?
He has logged off.
Okay.
Do you want to say something for
we will be back in the fall
with
a new series.
Yeah, yeah. So please stay tuned and subscribe to our newsletter. Okay, thank you. Thanks, everyone.
Thanks.
See you.
Everyone.
Have a good summer.
See you.